All right. Good morning. Let's get started. Do you have any questions before we start? Okay. So last time, we were still discussing, right, we're finishing up 8.7. Order stats, where the setup is that we have x1 up to xn IID with population density as some kind of given function. Okay. So actually, let's talk about some fine points, okay, about these kind of assumptions and all the details about all the stats. So first of all, right, do notice that the results we discussed so far in this section means that the random variables, okay, the xi's are continuous random variables, okay. Now, this is just a technical condition, all right. This is a technical condition to make things easy. To make the result, to make the derivation convenient. So you just kind of want to appreciate why, right? We do not want to discuss discrete random variables, for example, okay? Why do we not want to discuss discrete random variables? Anyone has any idea? What's wrong with having order statistics for discrete distribution, like binomial or Poisson? I mean, they're relevant, right? Why don't we want to do it here? Yeah, but what is the complication? Can you point out one complication that will happen in the discrete case that does not happen in continuous case? No, that's not. We deal with some all the time, right? I mean, if that's the case, then we don't want to deal with discrete at all, because that condition applies to any other kind of question. Okay, so the complication, all right, there is some complication, that's correct, but the complication that will arise, right, from discrete to continuous is this. If you have discrete distribution, guess what will happen in your samples? There could be ties. All right, in continuous random variables, right, there cannot be any ties. Oh, like suppose you have random variables like this: 1, 1, 2, 3, 5, 5. Then the max is 5. The min is 1, right? But there are two values that attain the max, two values that attain the min. You think about, right? When we discuss the max and the min, remember we say if the max less than some number, right, then everything else must be less than that. But if there are ties, you have to count how many ties there are. Agree? Because each tie kind of change the way that the max will appear. You understand what I'm trying to say? Just think of the logic that we derive this, the max, the min, and any other stats, right? The fact that there are some other members that can obtain the same values as whatever that order stat you're looking at cause you to have to consider the combinatorics, right, of that distribution, which again, right, I mean, in what Christine was saying is complicated, or Just simply speaking, not something we would like to get into. But in continuous random variable, right, there's no tie. So do appreciate that, all right? The fact that there's no tie means that it's a clean value. It's a unique value that only, right, at that point that random variable attains, all right? So that's all I want to make. Not that we cannot deal with all the stats in discrete distribution, but if you want to, then you have to think about, right, what if ties happen? Okay, how many ties there are? And that becomes a combinatorics question that, again, you can work it out, but not something we're interested in because the point of this class is stat, right, not combinatorics. Okay. Anyway, so having made that comment, any question on this? Okay, having made that comment, right, then we have a very general result, right? This is a, I guess in the spirit the language I was using is the universal result that the density, okay, of the ith order statistics, or I think last time I used K, right? Let's say K, will be, right? So I suggest, okay, that you always try to remember the rhyme and reason of the formula we put down. It just helps you to get a hold on the problem you're dealing with. So basically, right, you have X here, okay? And what you're saying is this is XK roughly. That means that there are K minus 1 values here and N minus K values here, okay? Whichever they are. So of course, right, the statement that XK is right smack on this value is a density statement, okay? And that means that right there, one random variable must take on that value. K minus 1 is less than that. So that's a probability statement. Right? And then N minus K is bigger than it. So all right. By the way, right, I mean, I write like this to make it precise, but in continuous distribution, whether or not you include the equality doesn't change anything. But usually we would like to have equality on the less, right, because it's CDF. Finally, right, this happens for any kind of combination, okay, that happens like K minus 1, N minus K like this. So you have to multiply with a combination number, which is N, choose K minus 1, N minus K. All right. And so the point I want to make is, right, this density right here, right, that I wrote down, exactly, it's just writing down whatever I see in the picture, no more, no less, okay? It's as easy as that. And of course, you have to also comment on the range, okay, on the support of the kth order statistics. And because we do not say much here, right? But of course you can say it. Basically the range of the support of the kth order statistics, right? Support means where the density is non-zero, okay? Support of the kth order statistics is the same, right, as the support of the population, okay, distribution. In other words, right, if the population was a uniform AB, then the range of this is also from A to B. If the population is a exponential, right, from 0 to infinity, then the kth order also takes value from 0 to infinity, right? I hope that's clear. Any question on this? And so So okay, let's talk about, right, what do we mean by this is universal result. Remember, when I say universal, what I kind of mean in this class is it's independent of the population distribution assumption, right? So that's roughly in that spirit, right? It's not really independent of the population distribution assumption, but whatever this is, okay, then you have the same, you use that hypothesis, you use that assumption in the formula, meaning that you do not require the population to be normal, exponential, uniform, whatever, right? Whichever you have the formula for it. That's why I say it's universal, okay? This result is not restricted to a family, or it's restricted to continuous family, okay? That's the only restriction we have, again, because of this technical assumption, technical condition. But otherwise, right, any continuous distribution, gamma, chi-square, beta, exponential, you have the density, you can put it down like this, okay? And it's true for any kth order statistics, including, right, the max, the min, the median, anything you want, right? So let's take a step back, all right, and see what we have and what we don't have. You want to always kind of, once you have a result, you want to kind of compare and contrast with the other results you have, okay? So compare and contrast with other, what do we mean with other results we have? Well, I mean, you know, the only other result we have so far is the sample mean, right, and the sample sample variance, right? So all the stats are some other kind of sample statistics. Type of results. So you see, here's the thing, right? And again, these are just some sort of meta statement that they're not meant to be precise or anything like that. They just meant to kind of show you the qualitative thinking observation you can look at to help you study this kind of material. What happens is, remember, with x bar and s square, right, the density is not explicitly stated. Remember, right? With x bar and s square, we don't state the density is not explicitly stated. I mean, for some cases, right, they are implied. For example, in the normal case, we say this is normal, this is chi-square. So it's implied. In other words, if you look up the density, sure, right, you have the, you know what it is. But for other kind of distributions, then we don't know the x bar distribution, we don't know the s square distribution, right? We said that. Here, right, again, in contrast, the order statistics, you see the density is explicitly stated. It's explicit in terms of the, you know, again, the population distribution, right, density, but it's explicit nevertheless, right? So the result you're getting is the density statement, okay? So all the statistics, density stated, right? On the other hand, a kind of very easy result for some reason is the first and second moment of the x bar and s square. I mean, maybe by second moment, I kind of mean variance, right? So expectation and variance, if you will. And I want to caution you a little bit, right? I mean, the variance of s squared does have some assumption, the normal assumption. But anyway, they're not that hard, okay? On the other hand, right, the order statistics, just try to run through your mind. If you try to compute expectation of this guy, it will not be that easy, okay? Just because of the calculus, really. Because you have to integrate this x to the some n, right? The nth order statistics. Oh, sorry, the nth moment. Let's say x squared, and you integrate this out. So you don't know what the density looks like. Density can be nasty itself. This probability can be nasty itself, right? Nasty is a sense that like the formula becomes kind of tedious to deal with. So notice that the moments, right? The moments of the order statistic is not something we just kind of give you, right? The moment not given, okay? So of course, right, that is a fertile ground for exam questions and homework and that kind of stuff, right? Because, well, it's not given, so you go ahead and calculate it for this case, all right? But of course, you see what kind of skill comes into calculating this. It's just simply calculus, all right? I mean, how good you are at integration. I mean, that's all there is. But on the other hand, right, do keep in mind that as the sample size get large, right, and the K or the statistics somewhere in the middle. Let's say you have a sample of 100, and you want to look at the 20th order statistic, right? Then this expression becomes pretty weird, right? I mean, like 19 here, 80 there. Who knows how to raise this expression to 80th power, that kind of thing. So the range of the kind of calculation we can do, again, depends on the assumption we can make, all right? And if you push it to a certain point, the complications start to get really, nasty that no one wants to look at. Anyway, right, just pay attention that the moment calculation is a question that has to be done on our own. It's not given as a theory. Well, so with that said, right, I mean, how would people even calculate the moments of order statistics if, like I said, it's pretty, not fun to do. So usually, right, I mean, numerical approach, right, like, you do a numerical integration, right? That's a topic of numerical analysis. That can be done because, you set up an integral, and then you, instead of calculating yourself, right, basically that's what someone was saying before, and you throw it to computer and ask the computer what the result is, okay? Of course, you get an approximation, but it's a pretty good approximation. Or, you can do simulation approach. So anyway, right, point being is this class is not about any of this topic. So I just want to mention that, right, the moment information of the order stats is something that, right, keep in mind that if I ask you about those kind of questions, it's a calculus question you have to calculate out by yourself. That's all there is, right? So I'm challenging you more or less on your calculus skills, but there's nothing that would be readily given by myself to you because I don't know what that is. Any question on this? Okay, so the next one we want to talk about, right, is using this picture, all right, using this principle, you can easily write down the joint density of the order statistics. Using the same principle, we can write down the joint distribution or the joint density of order stats. Okay, so in other words, for example, suppose you have some xi order stat and xj order stat. Okay, as a pair of random variables, what is their joint density? Okay, so in your quiz, for example, right, in your quiz, or even the homework, right, the textbook, if you just look at the problems in a textbook for this section, you see that what they care about is the min and the max. I guess this makes the most sense. The reason is from here, right, you can derive the difference between these two, which is called the sample range, which, right, again, is what people usually care about, right? The sample range, as you can see, is an estimate of the support length, right? The size of the support of the density. So anyway, right, the point I want to mention is, yes, right, the joint density of the order statistics, the joint behavior of the order statistics is something that is of interest to people. Again, you should set aside the difficulty in calculation. Difficulty in calculation is one thing, right? That's calculus. But conceptually, these things are not hard to write down, like in terms of thinking about how to write down the form. Again, right, the picture is clear. Here's I, right? Sorry. So let's say I plug in, right? I plug in value X and value Y, okay? So X for the ith order statistic and Y for the j order statistic. And let's suppose that I less than J, okay? So here's X, here's Y, right? So I want the ith order statistic to be smacked right there. I want the j order statistic to be smacked right there, right? That means that what? There's an I minus 1 terms below X. There's a j minus I terms in between. And there's the n minus j terms above Y, right? And of course, I mean, when you do the min and the max, then, right, there's nothing above and below. There's only n minus 2 terms in between, okay? But so when you write down this, right, you write down something like f of x at x for this term, f of x at y for this term. You write down, right, probability that you are less than x raised to the I minus 1. Sorry, right, I'll continue here, times, right, probability that you are between x and y raised to j minus I. And you write down the probability that you are bigger than y, sorry, no greater, right, raised to the n minus j, okay? So I hope you see that that's just describing exactly what I'm saying here. But of course, then you need some kind of combination number to count, right, how many possibilities that this can happen. So, you know, kind of flash news, my combinatorics is not that good. I'm not trained in combinatorics, so I'm not gonna write down the number right here for you because I think there's a chance that I will make a mistake. But something like n choose I minus 1, j minus I, n minus j, something like this, I expect. But, you know, I might miss some order. So I won't, you know, write it down explicitly for you. Of course, being that's the case, I won't really, you know, press this kind of point on the exam either. But I want to tell you that, right, it becomes a combinatoric statement. You understand? It's just a combinatoric statement where you just have to see how many possibilities you can arrange this arrangement. The probabilistic statement is very simple as far as I can tell, right? Smack a value on x, smack a value on y, I minus 1 below, j minus I in between, n minus j above. Okay, so that's what I want to say. And again, right, because we do care about joint behavior as well, not just kind of marginal behavior like this. Any question? That could be a sign of my combinatorics, weakness right there. Is it j minus I minus 1? How many terms are there in between? You're right. I mean, it could be, right? It could be. I think maybe I just miscount. Do people agree? Is j minus I minus 1? Or is j minus I? In between, right? In between. You're right, j minus I minus 1. The reason is, right, that basically all these guys must sum up to n. Yeah, thank you, right? Yeah, I'm true to my words. I'm not very good at this. But give me time, right? I will see my mistake. But anyway, I hope you see the philosophy, that's all. Any question? Right, I do know that 1 plus 1 plus this plus this plus this must be n, because you're basically describing n, the behavior of n, right? The n tuples, that's all. Okay. All right. So now let's focus on, so the order stats, all right, of important to us are the order stats that will be popular for us, okay? is the sample min, sample max, and the sample median. All right. All right. I don't know. Let's see. One, this. No, it should be j minus I. Okay. Wow, people really care about this. 1 plus 1, right? Plus j minus 1. Let's say plus j minus I minus 1 plus n minus j. It seems to me to be equal to n, right? No, it's fine. You see exactly that this is not the kind of thing that I want to flash in front of you in the sense that I'm not good at this, right? So I can make mistake, you can make mistake too, it's fine, right? There are things that we need to really work out on papers at home. But the point being is I'm showing you the philosophy of doing this, and I think you guys getting it, right? You corrected yourself, right? Once we know what we expect, making error is not a big deal, right? We can correct it. But I hope like something like this is fine, right? But of course, still, right? What is this combination number? You think about it, all right? I mean, I think this combination number is fine, like that kind of thing. But I think the order here matters. So, yeah. All right. So the order stats, right? That matters to us are these guys. It's just because it's simple and it's I guess it's popular, right? Also because they will be, right, for most of the distribution we deal with, they will be estimators. Okay, so we'll talk about that. But I want to mention that so you want to kind of know these guys very well, but order stats that are often used, right, out there, right, in practice, people care about sample quantiles. Okay, and I'll stop at that. I mean, any of you have taken, SAT, GRE, that kind of thing, you definitely have seen quantiles, right? You care what quantiles you fall in. But, I'm not sure if you ever connect sample quantiles with order stats, but sample quantiles is really order stats, right? For example, I guess the min is the 0% quantile, and this is the 100% quantile, right? And this is going to be the 50% quantile, right? But of course, 20% quantile, 75%, 90%, that kind of thing, right? People care about, but they fall under the sample quantiles, all right? Which I'm not going to go into. What is the symbol between x1 and x bar? There's no x bar. You mean x tilde here? This is sample median. This is sample max, right, for the parenthesis n, and this is sample min. Is that your question? All right. Yeah, the tilde, x tilde stands for the sample median, not the sample mean. Sometimes they should not be the same for a sample. All right. Anyway, so we won't talk about sample quantiles, but if you have time, you definitely want to kind of look at that and connect them back to order statistics. So we talk about the min, we talk about the max. All right, let's talk about the median. So for the median, it's convenient to assume that the sample size is odd. Okay. The reason is if the sample size is odd, then the sample median, right, will be I believe the k+1 order statistics, right? For example, if k equals to 1, n equals to 3, right, then the second, right, the value in between is the median. Okay. Now, what is the density of the median? Well, you see, because the median in this case, right, being the an order statistics, you can just write down. And actually, you see, if you care, you can just um, you know, draw the picture, right? This is x value smack right in between, and then there are k values right below it, there are k values above it, right? So the density of the sample median would be, right, n, which is 2k plus 1, right? Choose k, 1k, right? And then k values below it, k value above it. So maybe let me just do this. It's the same. And then the density. Okay, so that's it. That's the median, right? There's some symmetry, right, about the median. Notice, right, that there's some symmetry about the median. I mean, if the distribution is symmetric, then there's some symmetry about the median, all right? But the question is, right, that again, why are we interested in the sample median, for example, right? Interest in the sample median right, from our point of view, okay, from parametric statistics, comes from, right, may come in for distribution that are symmetric. Okay. For example, right, let's just take the normal because that's what the textbook kind of does. Let's say x1 up to xn, IID, normal, mu, sigma square. All right. So we have discussed that, right, the population mean, of course, is mu, but the population median, mu tilde, is also equal to mu, right? Because the normal distribution is symmetric around mu, right? Like that. So 50% below mu, 50% below mu, so mu equals to mu tilde. All right. So that means, right, to estimate mu and estimate mu tilde is the same thing because they're the same, right? So, but of course, when it comes to sample, right, when it comes to sample statistics, these are different values, right? X bar is the sample mean, is meant to be estimated from mu. X tilde being the sample median, right, is meant to be the, let me write a crazy symbol here for you, right? Mu tilde hat, meaning the estimator from mu tilde. But right, of course, because they are the same here, the point I want to make is that the sample median is also a possible guess, right? A possible estimator for mu. Is that okay? So when you have two choices like this, you obviously want to ask which one is better, or at least you want to compare, right? You want to compare the behavior of these two statistics to see how they interact in terms of, right, they being the estimator for mu, okay, for the population mean. With X bar, right, it's easy. We have done that before. We know that X bar is unbiased, or, you know, in general, right, is on target to mu. The spread, right, or the error you can commit when you estimate using X bar is proportional, right, to inversely proportional sample size. and proportional to how wide the original, right, the population distribution is. Fine. Well, of course, these are all knowledge, right? The new one, of course, is this guy. Is the sample median generally on target? And what about, what kind of error do we usually commit? Okay. And so I want to bring this up because obviously you see that this question in the next chapter, chapter 10, will become, formalized, right? This is a question of the biasness of the sample median. This is a question of the efficiency of the sample median, all right? But I want to put a question mark here in the sense that, right, connect back to what I said before. The moments, right, the moments of the order statistics is not something we can just hand out, because, right, what it takes is you need to integrate this. You need to integrate this, all right? And that is not something, right, we can just do it right away. On the other hand, all right, I'll tell you this, that for the case of the normal, or for the case where the distribution is symmetric around, mu tilde or mu, this you can prove, not very difficult. You can show that is actually equal to mu by symmetry, okay? And I'll either leave it as a quiz or, I'll ask you guys to just think about it or whatever. But this question can be done when you have the symmetry of the distribution. You can argue it out. Like basically you just observe some cleverness, you observe something nice about this integral and you deal with it. This one though, is something that, it's going to be a nasty calculus for general calculation, okay? So in other words, you can squiggle by with the expectation, with the variance, yeah, okay? So the message is, right, that in general, right, the explicit calculation of the moments of the order statistics, again, is something that we cannot put down in formulas. But, all right, that goes into the other, theme that I was saying in statistics, that exact results, you try to get them when you can, like this. But in general, right, exact result is hard. So you try the asymptotic approach, meaning that you let the sample size get large. In this case, you let k goes to infinity. Remember, what is k? K is the, k is this guy right here, where 2k plus 1 is our sample size. So if k goes to infinity, sample size goes to infinity too. All right. I say k goes to infinity here because I want to highlight the fact that we are only discussing the odd sample size. We're not discussing even sample size, okay? Because even sample size, the sample median doesn't have this form. But anyway, as the sample size goes to infinity, then the sample median is approximately a normal random variable with mean equal to the population median and variance equal to this guy right here. Like that. Okay? So, all right, what's going on here? First of all, right, this is the population median. So as it says that as your population get large, your sample median is close to your population median. All right, so it's consistent in that way. How large an error are you committing? Well, so ignore this for now. These are some kind of constant, scaling. It's still kind of proportional to the sample size, right? Inversely proportional. Of course, this is not n, okay? This is not n, this is k. This is the kind of half the sample size. But, proportion-wise, we don't care. It's inversely proportional sample size. What is this? This is the height, okay, of the density at the median, right? This is the population density right here. So this is the height of the density at the median, okay? So of course here, because you divide by it, you should assume that this guy is non-zero. So for example, this quantity right here will be exactly the height in the normal curve, whatever that is, right? So this right here, this value will be the one that we plug in, this value, okay? But in general, okay, whatever that is, you plug in. One more thing, this result actually is universal. In other words, it does not depend on normal assumption. In other words, all right, any sample median, I mean, we still talk about continuous distribution, okay? Any sample median of continuous distribution, when the sample size get large, and as long as it's an odd sample, then it will be consistent. And this is the variance. So in other words, right, this question mark right here can be plugged in like this. Of course, only when you have to guarantee the sample size is large. Okay, so that's the approximated answer to this question that we talk about. Okay, and that's the value of the asymptotic. This result is written in the book. Okay, it's not some of the asymptotic results I just tell you on the side. This one is written in the book, so they care about this result. So there, right? This is the answer right here. But of course, you need large sample size. Any question? Okay, so we will revisit this, all right, on chapter 10. For now, I mean, just try to kind of put all these pieces of information together and you know, see the meaning of it, okay? Now I will show you, all right, kind of a simulation of this result. So hopefully bring some visual for you. So let's see. All right, here. So what I'm doing here is I take a uniform, all right, from 0 to 1. You can see the Python, right? Let me know if you can't, okay?
Yes.
Okay, thanks. Uniform from 0 to 1. I look at the sample max. I look at the, and I look at, you know, this is the theoretical density. Okay, this is the formula that we described, right? And of course, I plot the sampling distribution and I plot the theoretical density to show you, right, that our result is correct, right? That is the density curve. That is the one that we write down in theory, matches, right, with the sampling distribution. In other words, the histogram, okay? And here the sample size is 3. This is sample max. Of course, you see it's tilted to the right, right? It's tilted to the right. It makes sense because this is sample max. It tends to be closer to 1 and closer to 0. Same goes for the sample, I think here's sample min, but I change the sample size to 5. So you see, I also have, right, the theoretical one. It's tilted to the left, right, and looks like this. Sample median, here, I think, let me just change to 3. All right, so no. So here, when k equals to 1, this is sample size 3. All right, so let me run that. So there, right, it looks like this. It looks like this. So actually, you see the normal, sorry, this is a uniform, right? The uniform is symmetric around its mean as well. So you see the median, right? The median density is also symmetric around the mean, right? You see, but it's like a invert square, right? It's an inverse square. Again, this is the theoretical, right, density. But here, right, notice this is small sample size. So this is the exact distribution that we're talking about. When, by the way, right, is my favorite question to ask you to compute the mean and the variance when the sample size is 3, all right? So when I put a question mark there for the variance of the median, that's when, like, you know, sample size is 100 or so, because the computation gets crazy. But when n equals to 3, all right, I think any one of us can do it, because there's only 3 terms in the density, all right? So I insist that when the sample size is really small, like your quiz, for example, you can calculate everything, okay? So be ready for that kind of question. But here, right, let's change the sample size to, I guess, 201, right? So this is kind of large. What we expect is what? That this will start to look like a normal curve, right, with small variance. You see? Normal. That's exactly that normal. And I said it's universal, right? Because I'm working with uniform here. I'm not working with normal population, all right? You see? And if you make it bigger, right? Let's say make it into 1,000, what happens? What happens is, right, this curve will still stay in the middle, right? The mean is still the median, which is 0.5 for the uniform 0, 1, but the variance will get tighter. Oops, I guess I run out of, I get too ambitious. Computer doesn't have that much. Let me see. Yeah, you see, notice the scale, right? It gets much tighter. All right. Now, any question here? Now, what may surprise you is actually the same behavior works for the max and the min too, I think. Let's try it, okay? The max and the min also converge to normal, but that's a different type of result. It's called Fisher conversions. Okay, hold on. X max is not defined. Oh, maybe. I need to run it here first. Oh, maybe I'm wrong here. Maybe it's not normal. Oh, it doesn't look normal. It's weird. I thought it does. It will be normal. Okay, so it doesn't look normal here. False advertisement, guys. I think I said something quite wrong. I don't know why. Okay, that's when sample size gets large. It doesn't look normal to me, but I do believe it does. It does go to normal. My fault. Okay, so I'm not. This is not in the book anyway. I was thinking that, but that doesn't seem to be true. So anyway, right, the median does converge to normal. Okay, that's the book's result. I do believe the max and the min should do that too, but it doesn't according to my picture. So I will revisit this and I will correct my result for you. Anyway, right? For now, it doesn't look like that, and that's what the result says. Any question? All right. So just some picture to hopefully bring the point home for you. All right. So we are done with chapter 8 for now. Okay. We still have, right, we still have 2 sections left that we will cover, namely the T and the F distribution. All right. But I will go back to them, right, when we discuss the confidence interval. So to be discussed later. Okay. Chapter 9 we skip. It talks about risk and measure of risk, which is a very popular statistics concept that kind of measures the again the performance of a statistics, I think, but the book somehow tends to go to statistical game or something. So they discuss concept of risk, which is not immediately relevant for our class. So the curriculum just skip it. So the next chapter we deal with is chapter 10. And the idea of chapter 10 is basically estimators, or if you want, point estimators. And their properties. All right. So for chapter 10, we will cover, of course, 10.1, 10.2, 10.3, and then we do 10.7, 10.8. That's the curriculum, all right? So that's what we follow. Except that I want to mention everything in chapter 10 is very good. Everything in chapter 10 is fundamental, all right, to statistics, including the concepts we don't discuss. Now, don't ask me why we don't discuss them. I think that's somehow the curriculum I get from the department. I guess because, the other concepts are a little bit outside the curriculum a little bit, or they don't want to give emphasis to it. But things like consistency, you have heard me saying, something about consistent, sufficiency, robustness, those are super good concepts. 10.9 talk about Bayesian estimation. Bayesian statistics is not something, is a kind of a different class a little bit, or sometimes people do mention it in a class like this, but it deserves its own treatment. So that's why we skip. But all these concepts, I'm just telling you that if you're in statistics, you probably want to take a look. They are really, really important concepts. In class, right, we only discuss this, all right? So anyway, let's tell you the story, right, of what we want to do here in chapter 10. So the story, right, is about point estimators. And so what is it, right? So the idea or the context is this, that you have, again, right, IID sample, we never deviate from that. And it comes from some population distribution, right? From some population distribution. Okay. And the population distribution could be, for example, right, normal mu sigma square, exponential lambda, right, or uniform AB, or let's say binomial, right, or Bernoulli P. Anyway, right, remember once upon a time we said we don't question the family. In other words, right, the family is given to us, or we think that's right. Now, of course, right, that's not quite realistic. People do question the distribution too, but that's not the point of this class. All right, we take the model as given, as in up to the distribution. We question, right, these guys. We question the unknown, right, population parameters. Okay, so mu sigma square or lambda or p, right? They are called the population parameters. And the emphasis, right, is they are constants but unknown. All right. There are sometimes the exceptions to them, but like say sometimes we deal with the case where mu is known, mu is unknown, and sigma square is known. But if that's the case, we will explicitly state that. All right. If we don't state anything, you should assume that they're unknown. All right. And so, of course, being unknown, right? The model is not determined, or you don't know the model until you know these numbers. So the process of calibration, right? Model calibration or the model estimation is exactly to come up with, right? Come up with statistics, right? As estimators, right? For these parameters. Okay, and I guess we have seen this so far, so it should not be strange to you. For example, x bar for mu, right? Lambda, x bar for lambda 2, and then I think here also x bar for p. But, right, s squared for sigma squared, for example. So they are called point estimators because basically, right, they are single value. They are supposed to tell you exactly what you think of that single number is. Point estimators will be distinguished from interval estimators or confidence intervals, right? Well, you're not saying what value you think they are, but you're saying what interval you think these values will stay in, all right? That's a different concept, right? That will be covered, I think, in chapter 11 or so. But anyway, right? So right now we just want to come up with one single value, right, as estimators for these guys. Now, of course, being statistics, right, they are random. Yes, because every time you have a new sample, you have a different estimator, okay? With the same formula, right? X bar for different samples are different values because X bar is random, that's what we say. So if it's random, right, what our question is will be, what are the properties, okay? Stochastic, right? Properties of, these estimators. And of course, right, when you say properties, you will want to define some properties that you care about and then, investigate whether your statistics, whether your estimators have those properties or not. The two properties we care about is biasness or unbiasedness, if you will, and efficiency, which is a topic of 10.2, 10.3. And then there's also a question of, right, when we say come up with estimators, how do we come up with them? Okay. So far, you have seen basically just intuition, right? Because mu is a population mean, sample mean is a good estimate for mu. Sigma square is a population variance, so sample variance is a good estimate for sigma square, for example. That kind of logic. So we want to formalize them, and we want to say that that's not the only way to think about them. So how to, okay, how to come up with estimators? Will be 10.7, which is called the method of moments. And 10.8, which is maximum likelihood estimator. Or as they're always called in the stat world, MLE. They're so popular that people don't even want to say them by the whole name. They just call it MLE, maximum likelihood estimator, okay? So anyway, that's the program, okay? How to come up with estimators and how to judge their properties, okay? How to judge the performance in some way, right? Because like I said, right, the more criteria you have, the more you can say about the properties. And that's why I say chapter 10 in general is very, very important because they list most fundamental properties. We only study 2, right? There are 3 more that we don't get into. Anyway, any question about this? Okay. So I will do things like this. Of course, by the order of numbers, seems like you want to do 10.2, 10.3 first, this later. I think it makes more sense to just discuss this first, and then we will look at the properties, okay? And then apply them to the methods. So I will do 10.7, 10.8 first, and then we'll go back to 10.2, 10.3, or kind of mention them simultaneously or something like that, as how I feel the lecture more naturally goes. So we will start with 10.7 today. Okay. So first, right? So let us just stay with an example. Let's say that you have x1 up to xn IID normal mu sigma square. Okay. So mu is unknown, sigma square is unknown, right? The question here is, what do we want to be the estimate for mu? Okay. And take a minute to think about this kind of question. It's not as innocent as it looks. The reason why it's not innocent as it looks is because there are more than one answers. All right. And that's exactly the whole interesting, the whole point of making this business interesting, that there's no single answer for estimator. Okay. In fact, the whole point is that it's infinitely many answers possible. And our job, right, is to filter through these choices and see which one is the best. And I guess best depends on situation. So the judgment is called for, right? Anyway, right, more than one possible answer is the message I want to make. For example, here you have seen that that's the case. For example, X bar and X tilde are both good guesses to begin with, right? But not only that, okay, not only that, what I want to make is this, that the definition, right, the definition of the estimator, I guess I didn't even give you a definition of estimators, right? But let's just give a formal definition. And by the way, right, you will see this notation, theta notation, theta. Theta will denote a generic population parameter. Okay, so when the book says theta, when I say theta, we mean it could be mu in this case, it could be sigma square, it could be lambda, it could be p, right? We just discussed a generic population parameter, and of course, right, theta hat, right, is a estimator for theta. So what do we mean by an estimator, right? So an estimator for theta, right? So the formal definition, an estimator for theta is just any statistic, or let's say a statistic, right? Any is too much maybe, is a statistic, right? That is meant to estimate theta. As far as I can tell. So in other words, right, this definition doesn't say much. And more importantly, it just say it's meant to estimate theta. Okay. So the emphasis is this, that I don't know if most students expect this, that when you look at a estimator, you kind of expect that there's only one, or this is the one, meaning there's no other choice. The point is that you can come up with anything that and you can claim that this is your estimator for theta. For example, right, in this example we're looking at, another choice that I can make is x1. All right, what is x1? X1 is the first value in my sample right here. I claim that x1 will be my estimate for mu. So a question for you, right? Is this a valid choice? Is this a valid choice? Let me see, how can I bring up? Why not? Yeah, I think I agree with Christine, right? It is a choice. Why not? I mean, right? I mean, I say it is my guess from mu. You may say that my choice is not the best, but exactly, right? When you say it's not valid, that you see what I mean? But then, right, when we say it's not the best, then it's quite it's quite proper to wonder, okay, what do you mean by not the best? In other words, you want to point out the deficiency, right? The weakness of choosing this versus, let's say, X bar. Okay, now you see the point of the question. By itself, there's no reason why you should accept or reject it. It's just a guess. But right, relative to some other choices, then you can say, okay, no, right, X bar definitely is better. But then, right, you want to point out specifically in what sense X bar is better. Is that okay? Or X tilde for that matter. Yes. Until you single out that criterion and say that's the case, any estimator could work, right? Is that okay? All right, and that by the way, right, is the point of 10.2 and 10.3, actually up to 10.5, right? You can see that X1 in the lens of biasness, in the lens of efficiency, how is it compared to X bar? Okay. But right, because of this kind of looseness of estimator, okay, 10.7 and 10.8 kind of gives a method, all right? And if you follow this method, then you should only come up with one answer because you follow the method, all right? So in other words, right, if I don't say anything, then you can come up with one, I can come up with one, anyone in this class can come up with one. But the point of 10.7, for example, is we want to come up with a method that would just give out one kind of estimator, and we would call that theta hat, moment or something. Oh, without, if it's too cumbersome, we just theta hat, and we understand, right, what method we're following. But the method, right, I guess one of the benefit of the method is that it just gives you one way to do it. Of course, if you employ a different method, let's say 10.8, you use MLE, you may get a different answer. But that's fine, right? Because now we understand which method we're following. And so we get what different kind of estimators, right? But without stating the method, right, you can see that whichever one goes. Not that that's bad. All I'm saying is if whichever one goes, then you want to use the criterion, okay, to compare them. Is that okay? All right. So method of moment, okay, what does it do? The method of moment is this. So suppose that you have a sample, all right? Or basically you have from a population, okay? Distribution that depends on theta 1, theta 2, etc. Let's say up to some theta k. All right. So what am I saying here? What I'm saying is the population, right, depends on more than one unknown parameters. Okay. That's a general case because you never know what kind of crazy distribution you're dealing with. Usually, right, k equals to 1 or 2. So usually you only have 1 or 2 unknown, right, population parameters like mu and sigma square. This is mu, this is sigma square, or lambda, which is 1, or a and b for uniform, right? I mean, I don't think I've seen too many 3 unknown parameters in a distribution. That's possible, but right, more than that. But here we're just describing a generic case, okay? So what happens here? What happens is this, that, so remember, right, by X, I mean a general, right, a generic random variable that has, right, the population distribution. So X is just some generic random variable that stands in for the population distribution. Basically, any one of these guys can be X, okay, because they come from the population. So what can I do with X? I can compute, right, and of course this is theoretically, expectation of X, expectation of X squared, all the way to expectation of X to K. Okay. So because my population distribution depends on these unknown parameters, these guys right here, right, will be also function of these unknown parameters. Okay, etc. So for example, all right, just to bring this point home and you don't think it's too abstract. For example, if the population is normal mu sigma square, then I'm saying expectation of x is mu, right? Expectation of x square is mu square plus sigma square. Is that okay? So that's my F1 and F2. If my population is uniform AB, then my expectation is A plus B over 2. My expectation of the second moment is the variance, which is B minus A square over 12 plus, right, expectation of the square, which is this square. Are we okay? All right. So these are just theoretical calculation, right? You can calculate these, but still, right, we don't know what they are. On the other hand, right, I will introduce something called the sample moments. Okay, the sample moments. So remember, right, basically you have x1 up to xk. All right, but now I would like to write them as lowercase, as sample values that we observe. Okay, so the kth sample moment will be defined as the sum of xi, okay, sorry, not xk, xn, because I have sample size n. Xi raised to the kth power run from 1 to n divided by n. Okay. Again, this is not something that's too crazy. For example, right, what is the first sample moment? It's a sum of xi over n, which is nothing but our sample mean. What's the second sample moment? Well, it's a sum of xi squared over n. Do we recognize this guy? Maybe not, right? Maybe not. But let's look at something that's a little bit right beyond the context, but actually it's the same thing here, which is a sample variance. Okay, what is a sample variance? So sample variance in this case, right? And by the way, it's a slightly different from the sample variance we've been discussing so far. The sample variance in this case will be, right, the second sample moment minus, right, this square. Okay. But you can verify that it's going to be equal to this. All right. So what is this? This is the S prime square that I mentioned before. In other words, it's the quantity that looks like S square, but the division, right? The division is by n instead of n minus 1. Is that okay? So the sample variance in this case, in the case of the method of moments, will be the division by n version rather than division by n minus 1 version, when we talked about the sample variance as we discussed before. So to save confusion, right, I will refer to it as s prime square rather than s square. Is this okay? Any question on this? So far we just defined terms, right? We define the population moments and we define the sample moments. All right. So, right, what's the deal? The deal is, again, remember, so the philosophy is this, right? Population moments are constant, right, but unknown. Sample moments are observed because you observe your sample, meaning you know it's known, right? But random. Okay. So ignore this for now. All right, we'll go back to this. The point is that, right, you have something that you're interested in but unknown. You have something that you can observe, and they kind of share the same idea. In other words, this is first sample moment. This is the first population moment. So the method moments say, you know, just equate them. Just equate them and solve for the unknown parameters. That's it. That's what it says. Okay. And when you solve for the unknown parameters, then you get the estimators. Okay. Then you get the estimators. Is more abstract than it really is. The method is very, very easy in practice because a lot of times things are just directly fall into your lap. Let me show you. Okay. For example, let's say x1 up to xn iid exponential lambda. We want to find lambda hat according to the method of moments, okay? What does it say? The method tells you that, okay, what's the population mean? Well, population mean is lambda, isn't it? Do we agree? Here actually is very important, right? It's very important for us to know what exponential we're talking about. Because here, right, exactly the population, the density is stated like this, right? If you state the other way, then the population mean is 1 over lambda, but here is lambda, right? And what's the sample? So this is population mean, right? What's the sample mean? The sample mean is x bar. So therefore, the method moment says, let lambda hat be x bar, period. That's it. Okay. So when we say lambda hat is x bar, we were implicitly following method moments without saying it. Let's look at another one. Okay. What is the method moments estimated for mu and sigma? And by the way, right, when I don't say anything here, I'm talking about method moments because we're discussing it in this section. Well, again, what do we do? What is the population mean, mu? What is the sample mean, x bar? What is the population second moment? Is mu square plus sigma square. What is the sample second moment is sum of xi square over n plus x bar square, right? So here, actually, you see a system of two equations, but the system is very easy, right? Wait, hold on, sorry, right? The second moment here, just this, sorry, right? This is second moment, sorry, okay? So, but it's so easy, right? Because here I already tell you that mu hat is x bar. Because mu hat is x bar, then what's sigma hat? Sigma hat is then this minus mu hat square, which is x bar square. But as we have said, this is like that. Okay. So I realize I go over time. Just one more thing. One last thing is, you see with the method moments, what do you observe? You observe that the population mean is really x bar as we expect, but the population estimator, right? But the variance estimator is no longer the sample variance that we used to say. It's not s square, it's s prime square. So the method forces you to use a bias version. That's just what the method does. Okay, so if you follow the method truly, then this is the estimator, not the n-1 version. Okay. All right, so we'll continue next time. All right. Thanks, guys. If there's any question, I'll answer. Otherwise, we'll see you. Yeah, thank you. You too. You too.